Good morning, dear students and friend. I welcome you again in the lecture series of subject EE145, that is Basics of Electrical and Electronics Engineering. See, during the lectures hours, we had already discussed the mesh analysis and the nodal analysis, right? And again, recall the fact that in the mesh analysis, we divide the circuit in the various meshes, which are the closed loops, right? And we write the mesh current equation, right? And its generalized form is R11, right? It is R11 I1 plus or minus R12 I2 plus or minus R13 I3 is equal to plus or minus V1. This is the mesh current equation for the first mesh, right? R11 is the sum of the resistances in the first mesh. R12 is the sum of the resistances which exist in between mesh 1 and mesh 2. R13 is the sum of the resistances which exist or which are common to mesh 1 and 3, right? I1, I2 and I3 are the mesh currents, right? And and is equal to plus or minus V1, where V1 is the sum of the voltages in the first mesh, right? And yes, here the plus or minus sign, we consider plus sign if the suppose this is the mesh 1, right? Here the mesh 2, right? This is mesh 1 and mesh 2, and our assumed direction of the current, let us say in mesh 1 is downward, and assumed direction, let us say this is I1, and assumed direction of current I2 in mesh 2 is also downward. So if the currents direction through this common resistance, right, both are same, and then we consider the positive sign. And if the current directions are opposite to each other through this common resistance R12, right, then we consider the negative sign, right? Now, and yes, in nodal analysis we consider the nodals nodes, it means principal nodes, to write the nodal voltage equations, and then we formulate the matrix, right? We know these facts. Now, let us proceed further. As per the rule in the mesh analysis, when you carry out the mesh analysis, then there must be the presence of the voltage source, right? Because we write this mesh current equations, and I1, I2, I3 are the mesh currents which are the unknown variables, right? And these resistances R11, R12, R13 and V voltages, they are the known variables, right? So see, suppose in some circuits the current sources are given, right? See, as we had discussed earlier, what are the meaning of current source? Which current source is a source which supplies the constant magnitude of current for the infinite amount of time, theoretically, right? And we know that the diode may act as a current source. Similarly, the transistor may be considered as the current source. Let us say this is IC, this is the collector current. So transistor may be considered as the current source. Now, in a mesh analysis, assume that the current source is given, right? And in nodal analysis, assume that the voltage sources are given, right? So if this happens, then we have to convert the current source into the voltage source and vice versa, right? So there is a rule, and this theory is known as the source transformation, right? Source transformation. Source transformation means we convert one type of source into the another type of source. Now let us say there is a DC voltage source, right? Let us say this is VDC, and in series with the VDC there is a resistance, let us say it is R, right? And here the some external circuit may be connected, right? Now this circuit is given. Now our aim is to convert this voltage source into the current source, right? So the requirement is there should be a resistance in a series with the voltage source, right? And yes, let us discuss in detail. See, if you consider any battery or any cell, right, which supplies, let us say battery is supplying 5 volt DC voltage. Now inside the battery, when the battery is connected with the load, let us say this is the load resistance RL, right, and this current I is flowing through this circuit, right. Now there is some internal resistance in the battery, and as a result there will be some voltage drop inside the battery itself. So mathematically battery is represented as the ideal voltage source. Ideal means there is no voltage drop. This ideal voltage source in series with this internal resistance. This is the internal resistance of the battery. Thickness, internal resistance of the battery, right? Every source has some internal resistance, internal impedance, and in internal resistance there will be some voltage drop, right? So the battery is practical battery is represented as battery in series with the series resistance. This is the internal resistance, right? Now this voltage source can be converted into the equivalent current source, right, by the following method. So instead of considering this battery, we consider this current source, or this current source. Battery is converted into the current source, right? And here, see, upper terminal is positive, so current is flowing in the upward direction. Be cautious about this. Current is flowing in positive to negative in the external circuit, right? So let us say this is A, B, C, D, right? So current is flowing in A, B, C, D direction. So current is flowing in upward direction. So this battery is converted into the equivalent current source I, right? And this resistance, series resistance, is now considered as a parallel resistance, like this. Same value, right? R ohm and R ohm, right? And this current source value would be, it would be I is equal to VDC upon R. So this is known, VDC is known, R is known. So take this ratio VDC upon R, it will give you I, and the magnitude of this current source is I ampere, right? So using this equation you can determine the magnitude of the current source, and direction is upward. This R is known, this is known, right? So between so equivalent circuit of the battery, or say this voltage source, is this current source in parallel with the resistance, right? Current source in parallel with the resistance, and vice versa. If current source is given and parallel to the current source the resistance is given, right, then this current source can be converted into this voltage source, right, and the value of the voltage source would be VDC would be V would be equal to I into R. So I into R, I is there, R is there, so multiply this I into R. So the value of the voltage source would be VDC, and this shunt resistance, parallel resistance, is now converted, or it is connected in series with the battery R, right? So this concept is known as the source transformation. So now let us see those sums in which the source transformation is required, right? So I have taken sums from the assignments, right? Right. This is the assignments. I have discussed some of the sums, right? So first of all, yes, consider this sum. Use the use the mesh analysis for this given figure and find out the voltage drop across each resistance and the current in the circuit. Now see this circuit. Here there is a current source whose magnitude is 0.5 ampere. It is flowing in upward direction. Then point A, then node B, and at node B 150 ohm resistance is connected. Between B and C 50 ohm resistance is connected. Between C and this reference node 100 ohm. Between C and D 250 ohm. And between D and E 100 ohm voltage source is connected. Right. Again, in this we want to carry out the mesh analysis, and the requirement for mesh analysis is it should contain only the voltage source. Current source is not allowed, right? So current source has to be converted into the voltage source. So yes, see, this current source is connected in parallel with this shunt resistance 150 ohm, right? Because both are connected between the same nodes. This current source is connected between A and the reference. 150 is connected between B, but B and A both are same because there is no resistance in between A and B. So actually the potential of A and B both are same. So this is actually a node. So 150 ohm resistance is connected between A and the reference, right? So this is a parallel connection. So convert this current source into the voltage source. So in rough side, yes, I have discussed these points already, right? So what would be the equivalent voltage? V would be equal to I into R. So I is 0.5 into R, it is 150, right? So yes, so V would be equal to 0.5 into 150, it is 75 volt. And direction, see, the direction of the current is upward, right? So this part, this upper terminal is positive. So this current source is converted into the equivalent voltage source, and upper node is positive, lower is obviously negative. Magnitude is 75 volt, right? So right, this is replaced. Now this shunt resistance will be considered as the series resistance, right? And remove this. So shunt resistance is now considered as a series. So it is connected in series with this battery, right? 150 ohm, right? So at B point, right, between this battery and B point 150 ohm resistance is connected, right? So this okay, this circuit, current source in parallel with the resistance is converted into the voltage source in series with that resistance, right? So equivalent circuit is this. Equivalent circuit of this is this one, right? So then from point B, connect the rest of this circuit, right? Then between B and C 50 ohm, C and reference 100 ohm, 250. Yes, here there is a voltage source, so there is no problem, no need to convert, right? So the equivalent circuit looks like this, right? Okay, so now there are two mesh. This is first mesh, this is second mesh. Now assume the direction of the current in each mesh. I assume the direction of current like this, clockwise. In the mesh 2, again clockwise, right? You can assume any direction, right? And in the exam paper, if the directions of the currents are given, then do consider those directions. Okay, now you can directly write the mesh current equations, right? So R11 I1, sum of the resistance in the first mesh 150 plus 50 plus 100, right? So it is 300. See this equation number 1, 300 I1, right? Now plus or minus R12 I2, sum of the resistance is common to mesh 1 and mesh 2, it is 100. So 100 I2 and plus or minus. So see the direction of I1 through 100 ohm is downward, and the direction of I2 through 100 ohm is upward. Both directions are opposite to each other, so negative sign plus is equal to plus or minus V1, sum of the voltages in the first mesh, and it is there is only one voltage, so it is 75 volt. And again If you consider the voltage source V only, then the current should flow from positive to negative in the external circuit. And see the direction of the assumed current I1, it is also from positive to negative in the external circuit. So both the directions are same. That's why we consider plus V, plus 75. So this is the first mesh current equation corresponding to the first mesh. Now the second equation, plus or minus R21 I1 plus R22 I2 is equal to plus or minus V2, right? So plus or minus R21 I1, so it is 100 I1. Again the directions are opposite to each other, so minus, plus R22, so sum of the resistances in the mesh number 2, so it is 250 plus 100, so it is 350 I2 plus 350 I2, it is equal to plus or minus V2, sum of the voltage sources in the mesh number 2. Okay, and there is only one voltage, so it is 100. Now plus k minus. See, if only 100-volt source is connected, then the current should flow from positive to negative in the external circuit. So in this case, it should flow in the anti-clockwise direction. Whereas we have assumed that the direction of I2 is clockwise. So both the directions are opposite to each other. That's why we put the negative sign. So 100 should be considered as negative. So as now these two equations are available, we can form the matrix, right? So coefficient matrix 300, minus 100, minus 100, 350, right? Coefficient matrix or R matrix. It is equal to I1 and I2 and it into I1 into I2 is equal to RHS 75 and minus 100, 75 and minus 100, right? So this is matrix R, this is matrix I, this is matrix V. So I would be equal to R inverse, take on this side, so R inverse into V. You can calculate, you can use the calculator, take the inverse of this matrix and multiply the inverse of this into this column vector, and ultimately you will obtain I1 as 0.17 ampere and I2 as minus 0.23 amps, right? Now I1 is obtained positive, that's why our assumed direction is correct. I1 is actually flowing in the clockwise direction in the first mesh. So in the last step, draw the resultant circuit diagram which shows the actual direction of the current, and ultimately you can find the voltage drop in each resistance. Now what about I2? I2's value, its direction, no, sorry, its value is negative. Negative means our assumed direction is wrong. What was our assumed direction? It was clockwise. So this is wrong. So what is actual direction? It is anti-clockwise in the mesh number 2. So in the equivalent resultant circuit diagram, not equivalent, resultant circuit diagram, I2 should be considered as anti-clockwise. I2 is flowing in anti-clockwise direction. In anti-clockwise direction. So this is the actual direction of I2, right? Okay. So now, so I1 is flowing in mesh 1, magnitude is 1.1711, right? So you can find the voltage drop across 150 ohm resistance. It is equal to I1 0.17 into 150, right? So you can find the voltage drop. Then similarly, I1 current is flowing through 50 ohm resistance. So voltage drop across 50 ohm resistance is equal to I1. It is 0.17 into 50, right? Okay. Similarly, consider mesh number 2. I2 is flowing through 250 ohm resistance, whose magnitude is 0.2368 amps, right? So voltage drop in 250 ohm resistance is equal to V is equal to I into R, so 0.2368 into 250. So you can find the voltage drop across 250 ohm resistance. And finally, voltage drop across a 100 ohm resistance, which is common to mesh 1 and 2. So actually, uh, through 100 ohm resistance, I1 is flowing in downward direction, I2 is also flowing in downward direction. So through 100 ohm resistance, I1 plus I2 currents are flowing, right? So I1 plus I2, so current through 100 ohm resistance is 0.17 plus 0.23, it is 0.4079 amps, right? And voltage drop across 100 ohm resistance would be equal to 0.4079 into 100. So it would be the voltage drop, right? So this is the mesh analysis in which we use the source transformation. Okay, now let us see the another sum. See this, it is taken from assignment 2. Use the nodal voltage analysis to find the potential of node A, potential of node B and potential of node C for the given figure. Again, this figure is given. Okay. There is a current source whose magnitude is 6 ampere and its current direction is downward. There is a node A. At the node A, 5 ohm, 15 ohm and 2.5 ohm resistances are connected. This is the principal node B. This is the principal node C, and at node C the 2.5 ampere current source is connected, and the lower node is the reference node, right? So yes, so see in this figure the principal nodes are given, but in the examination the principal nodes may not be given. So in the first step, identify the principal nodes. And I want to reiterate the fact that principal node is a node at which more than two circuit elements are connected together. So this A node is a principal node because at this node, this and this branch are connected, three branches are connected. At B node, three branches are connected. At C node, three branches are connected. And the lower node is the reference node at which in this case 1, 2, 3, 4, 5 branches are connected, right? And this is a reference node, and we assume that the potential of the reference node is 0. So we write all the equations with respect to these reference nodes, right? So the principal nodes are actually 4, A, B, C and reference, right? 4 principal nodes are there, but we consider one node as the reference, right? So we write the equations, nodal equations for total n minus 1 principal nodes. So there are total 4 nodes, 4 minus 1, 3 nodes in this case. So we will write 3 nodal equations in this case, right? So first step is identify principal node. Now second step, in this we want to apply the nodal analysis or KCL in other words, right? Uh, uh, the basic requirement is the circuit should contain the current source. It should not contain the voltage source. And if it contains the voltage source, then convert that voltage source into the current source. No problem. But yes, in this case, this circuit already contains the two current source. Then so there is no problem. Now, for each principal node, we will write the nodal voltage equations. Again, in step number 3. Assume the direction of current in each branch. Again, I use the word assume. So in this case, I have assumed that current in this resistance is flowing from A to from right to left between A and B, right? In a 2.5, I assume that current is flowing from A to B, and for this resistance in downward directions, right? Similarly for B, similarly for C, etc. Right? Okay. And yes, if any current source is given, right, then in that branch try to assume the direction of current which is same as that of the current source, right? Otherwise you will have to put the negative sign, right? See, in this case the current is flowing in downward direction. That's why I have taken the direction of current in 5 ohm resistance like this from right to left. It means it is also in downward direction, right? Okay, now let us apply the KCL equation or nodal equation for the node A, right? Okay, so this and this, so there will be three voltage equations. Okay, right? Now for this, what is KCL? Summation of the incoming currents is equal to summation of the outgoing currents, right? So see, in this node A, we have assumed that all currents are outgoing, right? So summation of the outgoing currents would be equal to summation of incoming. Incoming is 0. So summation of outgoing would be equal to 0 in this case. Okay. Now current in this 5 ohm resistance is what? It is 6 ampere, right? So algebraic summation of outgoing currents. So 6 amps, right? 6 amps plus. Now consider this branch. We assume that current is flowing from left to right. So obviously the potential of A should be higher than B. So it is VA minus VB upon R. VA minus VB upon 2.5. Right? I is equal to V by R. And then this VA minus 0. Right? We assume that current is flowing in downward direction. So obviously the potential of A should be greater than that of reference node. So VA minus 0 upon 15, right? So this is the summation of outgoing currents is equal to summation of incoming. There is no incoming, so it is obviously 0, right? So simplify this equation in terms of VA VB. So you obtain this equation: 0.4 VA minus 0.4 VB plus 0.0666 VA, and take this on right hand side, so minus 6, right? So this is Y into V is equal to I, current I. Okay. Uh, again, yes, simplify. This is VA, this and this, right? So 0.4666 VA minus 0.4 VB, right? Plus I put 0 because we have the three nodes, right? So plus 0 corresponding to VC. Of course, I should write plus 0 VC is equal to minus 6. So this is first nodal voltage equation. Now let us write the nodal voltage equation at the node B. Please pause this video and try to write the equations by yourself. Then only you will get the confidence. Okay. So let's start from this. For node B, we assume that current is flowing from right to left, right? So obviously VB is higher than VA, right? So VB minus VA upon 2.5, right? VB minus V upon 2.5 plus this VB minus 0 upon 20, VB minus 0 upon 20 plus, in this case we assume that current is flowing from B to C, so it is VB minus VC upon 6. VB minus VC upon 6 and is equal to 0, right? So this is second equation. Again, simplify this, so you will obtain this and ultimately you will obtain this minus 0.4 VA plus 0.616 VB minus 0.166 VC is equal to 0. So equation number 2 corresponding to principal node 2, principal node B. And finally, apply the KCL or nodal analysis for the principal node C. In this case, it is VC minus VB upon 6 plus VC minus 0 upon 4, right? So summation of outgoings is equal to summation of incoming. So it is equal to 2.5. So see, 2.5 is incoming, right? These are outgoings, this is incoming. So summation of outgoings, this is equal to summation of incoming. So it is 2.5. So again simplify this equation. So you will obtain this and ultimately you will obtain this 0 minus 0.166 VB plus 0.4166 VC is equal to 2.5. So this is the nodal voltage equation for the third node, that is node number C. Now arrange equation number 1, 2 and 3 in the matrix form, right? So this is the coefficient matrix, right? Where is the equation number 1? This. So coefficient for VA, then this is VB, this, sorry, this VA, this is VB, this is VC. Coefficient of VA is 0.46. So 0.46, coefficient of VB, can go to equation number 1, yes, minus 0.4. So it is minus 0.4, and coefficient of VC is 0. So it is 0, right? Then the column vector VA, VB, VC, right? Then the right equation number 2, this minus 0.4, 0.6, and minus 0.16, right? So second row as well as the third row corresponding to the, and see the equation number 3. So first is 0, 0, minus 0.166, 0.166, 0.4166, 4166, and right. So this is the coefficient matrix, this is the column vector VA, VB, VC, right? And then the RHS. So RHS is minus 6, then it is 0, right, minus 6, then 0, and then 2.5. So 2.5, right? So this is nothing but it is AX into B, right? So X is equal to what? This matrix is equal to what? A inverse into B, right? So take this matrix on this side, take its inverse, multiply that inverse with this matrix using calculator, and ultimately you will obtain VA, VB, VC, right? So VA magnitude is minus 30.04, VB is minus 20, and VC is minus 1.986, right? So as VA, VB, VC are found out, right, you can find the current in each branch, right? So current in this 2.5 ohm resistance is what? VA minus VB upon 2.5, right? Similarly, current through 20 ohm resistance is what? VB upon 20, VB upon 20, right? So this is the sum of the nodal analysis, or you can say the KCL, Kirchhoff's current law. Now in this case, interesting point to notice is the signs of VA, VB and VC all are negative. It means, please pause this video and try to answer. The negative sign indicates what? Yes, the negative sign indicates that the potential of A is negative, means the potential of A is lower than this reference node. So reference node's potential is higher than the potential of A. Reference node's potential is what? 0 volt, right? And that of node A is how much? Minus 30 volt. So the potential of A is lower than that of reference node by 30 volt. So see in the homework, draw the resultant circuit diagram in which the actual directions of current should be indicated. So it is interesting to note that the current in through 15 ohm resistance will flow in the upward direction from this reference node to the node A, because the reference node potential is higher than that of node A. Similarly, through 20 ohm resistance, see the potential of node B is, it is minus 20. So current through this 20 ohm resistance will flow in the upward direction from reference node to the node B, because the potential of reference node is higher than that of node B. So current will flow in the upward direction. Similarly, VC is also negative, minus 1.96. So current through this 4 ohm resistance will flow in the upward direction from reference node to the node C, because potential of node C is lower than that of reference node, right? So I have told you the direction of current through this branch and this branch all are in upward direction. Similarly, you can determine the direction and magnitude of currents in these branches, and you can find the voltage drops. Okay. Okay, now let us see this sum. It is taken from assignment 2. See this figure. Here, in this figure, we have to apply the KCL, and ultimately we have to find the current supplied by this 5-volt battery. So this circuit consists of 1 ampere current source which is flowing in upward direction. There is a node A. At node A, 5 ohm resistance and 2 ohm resistances are connected. This is the node B, 4 ohm resistance and 20 ohm resistances are connected. This is the node C, a 10 ohm resistance, and between a C and reference node, 5-volt battery with a lower terminal positive, upper terminal negative are connected. So we have to apply the KCL. So in the first step, identify the principal nodes. So this is a principal node, this is a principal node, this is a principal node. So there are 3 principal nodes. Okay. Now, again the KCL, for applying the KCL, it should consist of the current source, right? So this consists of the current source. But in this, it also consists of the battery, and in the problem, it is asked that find the current through the battery. So we cannot convert this battery, this voltage source into the current source in this case. Why? Because see, for converting the voltage source into the current source, we require the internal resistance of the battery, and internal resistance is connected in series with the battery. So in this case, no internal resistance, no series internal resistance of the battery is given. So we cannot convert this voltage source into the current source because no series resistance is given, right? So no problem, keep this voltage source as it is, and finally we will do some mathematical operations to find the current. So no problem, right? You can convert the voltage source into the current source if and only if the series internal resistance in series with the voltage source is given, otherwise not, right? Okay, no problem. So again, for each and every principal node, we will apply the KCL. So again, pause this video, try to write the KCL equation, nodal equation for the given directions of the current. These are the assumed directions of the current, right? So for the node A, right, summation of incoming currents would be equal to summation of outgoing currents. So for this, VA minus VB upon phi plus VA upon 2, it is equal to 1, right? So this is the equation. Then simplify. So you will get equation number 1. 1 is equal to 0.7 VA minus 0.2 VB. Now apply the KCL at node B. Again this. So summation of the incoming currents is equal to summation of the outgoing currents. So start from here. VB minus VC upon 4. क्या say? Yes, VB minus VC upon 4 plus VB upon 20. VB upon 20, right? Summation of outgoing currents is equal to summation of incoming currents. So I have assumed that current is flowing from A to B. So obviously it is VA minus VB upon 5. VA minus VB upon 5. So again, simplify these equations, right? So this is the simplification, right? Try to cross check this and you will obtain this equation, second equation, 0.2 VA minus 0.5 VB is equal to 1.25, right? And finally apply the KCL at node C. So again, summation of the incoming currents are equal to the summation of outgoing currents. So again, for this VB minus VC upon 4 for node C, yes, KCL at node C, VB minus VC upon 4 plus VC upon 10, yes, summation of incoming. There is only one incoming current, right? So it is finished. So summation of incoming currents is equal to summation of outgoing currents. So VB minus VC upon 4, it is equal to 4 equal to outgoing. Yes, VC upon 10 is equal to VC upon 10 plus this current. This current is assumed to be the battery current, and I denote this current through the 5 ohm battery as I battery or IB, right? We have to apply the KCL, that's why we have to consider the current. And I assume that this I battery current or IB current is flowing in this branch. So this is the new point, right? So we have to consider KCL, so consider the current. So it is IB or I battery. Again, now simplify this equation in terms of VBVC, right? Okay, so there are three equations, right? This is equation number 1. It is in terms of VA and VB. This is the equation number 2. It is also in terms of VA and VB. So there are two unknown variables, VA and VB, right? So two equations, two unknown variables. So solve these two equations first, right? So solving equation 1 and equation 2, right? I have again written this, right? And I have multiplied this equation by 0.5 and this equation by 0.2, and ultimately I have solved these two equations, and ultimately I got VA is equal to 0.8064 volt, right? And substitute the value of VA in either equation 1 or 2, and ultimately you will obtain VB, right? This is the steps. So you obtain VB as minus 2.18 volt. Once you obtain VA and VB, you can solve yes, this equation, because this is the equation which considers VB and VC. So VB is known, VC is known, VC is known, so you can find the battery current IB. So finally, the KCL which was applied at node C, equation number 3 is solved. VB is known, VC is known, right? All are known. And ultimately you find the I battery current. So the current supplied by the battery is 1.205 amps. And be cautious about the signs. We have obtained VB as minus 2.18, right? So pause this video and try to answer what is its meaning. The meaning is the potential of node B is lesser than that of the reference node, right? So when you solve these equations, we have to consider VB as a negative, because we are considering the algebraic additions. We do consider the sign convention, right? So VB is considered as a uh, minus 2.18, right? And VC is right, and we have obtained VA can say yes, VA as a positive 0.8, right? So the potential of A is higher than that of the reference node, right? So of course through 2 ohm resistance the current will flow in the downward direction, because the potential of A is higher than that of the reference node, right? So be cautious about the sign convention, right? VB is obtained as negative, so consider this value as a negative, right? So the battery current is 1.2 amps. Now see this circuit using the nodal analysis and find the currents in the various resistors of the circuit given below, right? So here first of all see that it consists of the current sources, so there is no problem. Identify the principal node, it is 1, 2 and 3, right? And this is the fourth node, it is the reference node, right? Again assume the direction of current in each and every branch, and you can write the nodal current equations, right? So uh, these are the assumed directions of the currents, right? Now pause the videos and write the nodal voltage equations for each and every node, right? This is the incoming current I, this is the outgoing, this is the outgoing, and this is the outgoing, right? So I will discuss the first nodal voltage equation corresponding to the first node. right? So it is equal to summation of incoming currents should be equal to the summation of the outgoing currents, I1 plus I2 plus I3, right? We can write I is equal to I1 plus I2 plus I3, right? Okay, so now I is equal to what? It is 10 ampere. 10 amps is equal to what is I1? V1 upon 2 plus V1 minus V2 upon 3, right? Plus V1 minus V3 upon 5. V3 upon 5. Now simplify this, you will obtain this first equation. And yes, exactly in similar fashions, you can write the nodal equations, KCL equations for each and every remaining nodes. And then you can solve this sum, right? So yes, in the PPT, I have already provided this PDF file, right? So you can cross check your results, right? Try to solve these sums by yourself, right? And ultimately you will obtain each and every current, right? Again, yes, this is a simple two principal node circuit and you can apply the KCL, right? It is well understood, so I will not discuss this. Okay, by using the mesh resistance matrix, mesh analysis determine the current supplied by the each battery for the following circuit, right? So we have to apply the mesh analysis. So first of all, see, mesh should contain the voltage source. So yes, this contains the voltage source, this contains the voltage source, this and this, so there is no problem, right? If there is a current source, then current source must be connected in parallel with the resistance, right? And that combination is converted into the voltage source in series with that resistance, and then you can proceed further. So these are the assumed directions of the current for each mesh, right? And for now, one by one, for each mesh you can write the mesh current equations, right? So see, you can write equation number 1, 2, 3, etc. directly, right? So what is R11 I1? 5 plus 3, 8 I1, right? 8 I1 plus or minus R12 I2, R12 I2. So common resistance between first mesh and second mesh is 3 I2, 3 I2. Now plus k minus. See, this 3 ohm, through this 3 ohm resistance, I1 is flowing in downward direction, out 2 is flowing in upward direction. Both the directions are opposite to each other. As they are opposite to each other, sign should be negative. So minus 3 I2 plus or minus R1 3 I3. Sum of the resistance is common in between mesh 1 and mesh 3. So there is no common resistance between mesh 1 and 3. So 0 I3, right? 0, okay. Yes, 0 I3, and it is equal to plus or minus V1, sum of the voltage sources in the first mesh. Algebraic summation of the voltage sources in the first mesh. Okay. Now, yes, there are two voltage sources, 20 and 5. Now be cautious about the sign. If there had been only a 20-volt source, then the current would have flown in clockwise direction from positive to negative, right? In external circuit in clockwise direction. And see the direction of I1, assume direction of I1, it is also clockwise, right? So both are same. So consider 20 as positive, right? And now what about 5 ohm voltage source? If there had been only one 5-volt voltage source, then the current would have flown from positive to negative in external circuit. So in this case, in anti-clockwise direction, right? Anti-clockwise direction. But the direction of I1 is, assumed direction of I1 is clockwise. This is clockwise. For 5 ohm, it should be anti-clockwise. So both are opposite to each other. That's why we put a negative sign. We put a negative sign for 5-volt voltage source. So it is 20 minus 5 plus 20 minus 5. Be cautious about this fact. Yes, now you can simplify this. You will obtain equation number 1. And similarly, you can write the equation number 2, equation number 3, you can form the matrix, and ultimately, yes, this matrix is obtained. R matrix into I matrix is equal to V matrix. So I matrix would be equal to R inverse into V matrix. So take the inverse of this, it is multiplied with this, you will obtain I1, I2, I3, right? Again, in this case, we obtain the I3 as negative 3.13 ampere, means our assumed direction is wrong. Actual direction is opposite to that of assumed direction. So what was the assumed direction I3? I3 was clockwise. So clockwise is wrong. So actual direction of I3 is anti-clockwise. So in the final step, draw the resultant circuit diagram which shows the actual directions of the currents. Right. So see, I3 is flowing in anti-clockwise direction. And we got, what about I1? I1 is 2.56 positive, I2 is 1.82 positive, so assumed directions are correct. So I1 is flowing like this clockwise, I2 is flowing in a clockwise direction, so no problem. Okay, so now this figure shows the actual directions of the currents. Right. So now you can start from here. Battery B1 20 volt. How much current is flowing through 5 ohm resistance? Only I1, and direction is from A to B, and magnitude is 2.56. Now through this 3 ohm resistance, which current is flowing? I1 in downward direction, I2 in upward direction. So actually only one current is flowing. Either it is I1 minus I2, okay, I2 minus I1. So always take bigger minus smaller. So which one is bigger? I1 bigger છે કે I2 bigger છે? I1 is what? 2.56. I2 is 1.82. So obviously I1 minus I2 should be taken, right? Because I1 is more powerful than I2. I1 is bigger. So I1 minus I2 current is flowing through 3 ohm resistance, and it is 0.74 amps. And direction should be taken as that of the larger current. Which one is larger? I1. So downward direction. So through 3 ohm resistance, current is flowing in downward direction, and magnitude is I1 minus I2, right? And this downward. And again, one by one, you can find the direction of current through each and every resistance. And again, at each and every node, you can verify the KCL. So summation of incoming currents, let us say at point G, right? Incoming current is 1.82 and 0.74, both are the incoming. So it would be equal to outgoing. So this plus this would be equal to 2.56 amps, right? So incoming would be equal to outgoing. And yes, this B1 battery is supplying the current. So we can say that this B1 battery is discharging, whereas see the B2 battery. In B2 battery, current is flowing into the positive terminal and it is coming out from the negative terminal, right? So current is not flowing from positive to negative in external circuit, but it flows in reverse direction. Means we can say that B2 battery is charging. It is being charged just like mobile charging, right? And B1 battery is discharging, right? So yes, I have solved this whole sum, right? Uh, you can cross check, right? Now in this case, find the mesh currents I1 and I2 in the circuit which is given below. So there is a voltage source, there is a resistance, there is mesh 1 and there is mesh 2. The unique point is it contains this uh, dependent voltage source as we had discussed in the classroom, right? So see, it is positive and negative, means this rhombus shows that it is a voltage source, but this voltage source magnitude is being controlled by 3I2. So it is being controlled by the current of the mesh 2, that is I2, So the magnitude of this voltage source is 3I2, right? So such dependent source is known as the current dependent voltage source, right? Or current controlled voltage source, CCVS. Current controlled, right? This current is controlling the magnitude of this voltage source, current controlled voltage source, right? So yes, so this is nothing but a voltage source whose magnitude is 3I2. Don't worry, right? So yes, you can write the mesh current equation for this mesh, right? I1 R11 I1 plus or minus R12 I2 is equal to plus or minus V1, right? So R1 R11, sum of the impedances resistances in first mesh, so 1 plus 1 it is 2 I1 plus or minus R12 I2, so 1 I2 is equal to plus or minus sum of the voltage sources in the first mesh. So here 4 volt uh, and the direction of I1, right? So current supplied by 4 volt and I1 both are same, so it is plus 4. And what about this dependent source? If this dependent source is acting alone, then current should flow from positive to negative in external direction, external circuit, right? So in anti-clockwise direction, but I1 is flowing in clockwise direction, both are negative, so we have to consider negative 3I2, right? That's all. So finally you will obtain this equation, 2I1 plus 2I2 is equal to 4. So you will obtain this equation, I1 plus I2 is equal to 2. Similarly, write down the mesh current equation for the second mesh and solve both the equations number 1 and 2, right? You will obtain I1 as 3 ampere, I1 as 3 ampere and I2 as minus 1 ampere. So actual direction of I2 is opposite to assumed direction. So actual direction is flowing in anti-clockwise direction, right? And the magnitude of this dependent source would be equal to 3I2, means 3 into I2. So 3 into 1, so it is 3 volt, right? This magnitude would be 3 volt. Again, in this sum, find the value of V. See this circuit, it contains this current source, current control current source, right? Because this indicates the arrow, it is in upward direction. Its magnitude is being controlled by I1, and I1 is the current which is flowing through 6 ohm resistance, right? And V is the voltage which appears across first node and the reference node, right? Now this circuit contains only one principal node. This node, this node, this node, all are same nodes because each have the same potential. Okay, so again you can write the KCL at each node. Assume the direction of currents. These are the assumed directions of currents, right? So okay, this is the 4 amps. So 4 amps plus summation of incoming currents at node 1, 2 I1. This plus this would be equal to outgoing. Outgoing is what? I1 plus this. It is what? Current through 2 ohm resistance. So it is current through 2 ohm resistance is what? V upon 2, voltage of 1. Voltage of node 1 is what? V, right? This V. Voltage of node 1 is given, this V is given, right? With respect to this reference node. So voltage current through 2 ohm resistance is V upon 2, V upon 2, right? So 4 plus I1 is equal to V upon 2. So V is equal to 8 plus 2I, right? Okay, and yes, now again this I1 can be determined. See, I1 is what? It is equal to V upon R. So I1 is what? The potential of node A, V1 upon 6. V1 is what? V, right? So I1 is what? V upon 6. So I1 is replaced as V upon 6. So in this equation, V is equal to 8 plus 2, 2. I1 is what? V upon 6. So simplify this equation. So you will obtain, simplify this, you will obtain V is equal to 12 volt, right? So V is equal to 12 volt is obtained, right? So V is obtained, and similarly you can determine this value of this current source to I1. I1 is what? I1 is what? V upon 6. Now V is of 10. 2 I1, 2. I1 is V upon 6 and V is what? 12 volt. So 2 into 12 upon 6. So 6 2s are 2 into 2, 4 amps. So value of the dependent source is 4 amps. Right? So these are the sums which involves the dependent sources. Right. So yes, this is the mesh analysis. You can write these equations, no problem. Yes, this is well understood, no problem. Right. In this case, the we have to apply the nodal analysis. Again, this is a principal node, this is a principal node, this is the reference node. Here in this case, the direction of the current is given. It is downward direction and its magnitude is given as minus 1.4 amps. Right, minus 1.4 amps is given. Right, again there is no problem. So there are two principal nodes. Right, we will write two nodal equations corresponding to node A and node B. Right, so see, if apply the nodal equation or KCL equation at node B, શું થશે? Please pause this video. It is VA minus VB upon 5, VA minus VB upon 5 plus VB minus 0 upon 1. Sorry, it is incoming, it is equal to outgoing. So incoming is only 1, outgoing is this as well as this. Right, so incoming is VA minus VB upon 5 is equal to outgoing VB upon 1, VB minus 0 upon 1 plus this magnitude, it is minus 1.4. So it is minus 1.4. Simplify this equation. Similarly, write the KCL at node A. It is what? Summation of incoming, it is equal to outgoing currents. Incoming is 3.1. It is equal to outgoing VA minus VB upon 5 plus VA minus 0 upon 2. Simplify this equation, you will obtain equation number 1 and 2. Solve this equation number 1 and 2, you will obtain VA and VB, and ultimately you will obtain the currents in each and every branch. Right. So yes, this is all about the sums of mesh analysis, nodal analysis, and mesh and nodal analysis in the presence of dependent current sources, dependent voltage sources, etc. So uh, thank you. Mm,